My name is Satya Gupta. Currently, I am serving as President of VLSI Society of India. I had good fortune of working at basically companies like Intel, developing the cutting edge technology, as well as working at the startup where new product and new innovative designs were done, and also work with the India ecosystem through founding the India Semiconductor and Electronics Association, VLSI Society of India, and other such organizations to build the right ecosystem for electronics and semiconductor in India.
I'm Wilfred, Intel Fellow. I'm mostly involved in creating the required technologies for our client data center, AI, and HPC products. I've been at Intel for 26 years, and I've created everything from their low power microprocessors to their highest performance AI HPC chips. And over the years, I've had the joy and benefit of creating things from process technology, packaging, memory, CPU architectures, and chipset and chipset architectures.
Good morning and welcome to Chiplet Charcha, an initiative by VLSI Society of India to bring together global technology leaders in the field of VLSI design, chips, and semiconductor technology. Today we have Wilfred Gome, Intel Fellow, to discuss about the what he has done at basically Intel and what is the future of the technology. So welcome Wilfred, and thanks for joining us for this episode of Chip Pe Charcha.
Satya, thank you. Good morning all. Really good, and I'm happy to be here, to be on Chip Pe Charcha and discuss some of these really important topics.
So just to give a little background about Wilfred, Wilfred grew up in Bangalore, went to St. Joseph's School, and then did his undergraduate at NIT Calicut. Followed that, he did his master's from University of Hawaii, and subsequently he joined Intel in 1997, and he has been there for about 26 years, and he has made remarkable progress to become a fellow at very young age and drove very critical programs at Intel, which basically will define the future of semiconductor technology and computing for Intel and for the rest of the world. So while I was just discussing with a couple of the colleagues, he is also known as the CTO, not in traditional term CTO, not Chief Technical Officer, but Chief Troublemaking Officers, as his colleagues like to call. So thank you, Wilfred, for joining. So we'll start with the...
Thank you for the introduction.
Yeah, welcome. I think you have done remarkable things basically through your career. So we'll start with getting to know a little bit of a background, how basically your growing phase in Bangalore, school and college life. If you can share some basically details about your early life and studies.
Mm-hmm. Yes, Satya. So first, I'm really happy to be back in Bangalore. This is my hometown. I went to school at St. Joseph's Indian High School, my pre-university at St. Joseph's College. In fact, what had happened is I was right from a very early young age, really interested in electronics. We used to go to KR Market, get some of these kits, build it at school. So what happened is when I was just graduating high school, St. Joseph's College started at that year a PCME program. So that was physics, chemistry, mathematics, and electronics. And that was the first time St. Joseph's College actually offered it. And I took that opportunity, and and I have to say that that batch and that class that I think was full of superstars. And I felt at the time like maybe, what would I do with my future? But since I took electronics, I was able to actually build many kits, many systems, and then I went on and did my electronics and engineering, and Then I went and did my graduate school. But what happened is, as I started assimilating some of these things, the theoretical aspect of it became really, really important to me. So I dived more into the materials, the circuit technologies, the physics. So finally, I went to school at the University of Hawaii, and the reason I went there is they had the best, programs across VLSI and computer CAD. And in fact, the University of Hawaii had a really good AI program at the time, and I actually did my graduate program in efficient representation of VLSI systems, and I did a lot of programming in Lisp and Prolog. And because of that, I got hired at Cadence, and Cadence had, they were developing a system for synthesis of Verilog. And with my electrical background and the fact that I knew programming, I started understanding, and I built this systems where you could synthesize, complex circuits. And then what happened is actually the Intel team in Oregon, they were working on this really interesting microprocessors, and they had circuits which were high-frequency circuits, domino circuits, and they needed help to actually synthesize it, and they recruited me to Intel, and that is when I met Satya, and there was a very small team, and it was a team full of superstars. There were professors from Caltech, Satya, there were folks who had come from IBM. We all had expertise in different fields, and we actually created a tool which could take high-level RTL abstraction and create an actual GDS which we could send to the fab. And in that experience, we actually created some both new methods, new circuits, new methodologies. And I remember Satya and I used to actually discuss some of those things at great depth. And one thing that happened is that because we really worked on these problems, we figured out that at a very high level of abstraction, that the entire flow of from the high level RTL to the GDS mattered. And then I was able to take this and create compilers for CAD, for register files and caches and other things.
So, what was the importance of the dominant technology for Intel processors at that point of the time? Why was it a critical technology? If you can basically give the benefits and what it brought to the Intel microprocessors, that will be good for the audience to learn about how did dominant technology, which was basically a program run under Barbara Chapel, and basically 8 or 10 of us, we basically did the different part of it. But just a perspective, why dominant technology is important basically at that time, and what is the relevance of it today?
Great. So actually, what is not known is many of the critical structures like register files and caches, they operate on what is called domino logic. And what domino logic means is these are monotonic circuits. They can be created using N-only transistors or P-only transistors. Essentially, in half the logic depth, you can get really high frequency and low power. So the teams, we were actually figured out to extend it beyond memory circuits to control circuits and data paths. For example, like an ALU, you could design a really complicated ALU with many logic functions, and then the output of it going into like a data path or a cache, all being done in much reduced logic depth. So the teams at Intel or even across the industry use this to create high performance processors, both emphasizing wider machines and higher frequencies.
So before the decal project, my understanding is the most of industry used to do domino logic in a handcrafted manner. Decal was the first effort to basically make it a domino circuit design in automotive.
That is right. Yes, that is. In fact, what had happened is, that project had many ramifications for Intel and the rest of the industry. First is, we were able to come up with methodologies to contain those specialized circuits into certain domains. Second is, the application of the techniques to memory circuits and regular data paths became really important, and you came up with compilers. So even to this day, there are islands in your CPUs which use high performance circuits, because there is absolutely no other method of like getting that performance. But long story short, the importance of like having a methodology with a good feedback loop from RTL to timing to layout, where you can get layout constraints, timing EVR constraints, having sizing. In fact, if you remember, we developed a sizer called LR sizer. It was a Lagrangian sizer, where you could actually create all the double derivatives. All those techniques are even now very important. Obviously, the variables have increased. Yeah. So the techniques that were created for circuits which had 1,000 gates now are applied to 1,000,000 gates, but the fundamentals are exactly the same.
Yeah. So just this decal project, which basically was very important for Intel, had created a lot of basically industry leaders. Wilfred started there and became the Intel Fellow. There was another gentleman, Satya, who became few years back managing director of Qualcomm India, and many other basically.
Actually, Satya, if you remember, let me give you some other examples. Yeah. Naveed, he was just a good colleague of us. Like, he's gone off and done many.
So Naveed Sherwani, who had basically I had partnered with him for multiple startups, yes. Post Intel. So a lot of basically good technologists and basically stars came out of basically this decal effort. So moving forward, right, after domino synthesis, right, you picked up automation of the register files and basically a couple of other things during your basically stint, right? And about 7-8 years back, you started looking at this whole idea of disaggregation the monolithic chips into basically smaller chips, which can be basically designed independently and then put together. So can you kind of explain how did that idea came? Because probably you and the Intel team were one of the pioneers in basically coming up with this idea. Obviously, other companies were also working in the similar thoughts, but how did basically this thing came that we should basically go from monolithic circuits to this basically smaller circuits which can be again put together, which is today popularly known as the chiplets, right? Yeah. How did this whole idea came about?
So Satya, a really good point that you bring this up. By the way, this has been a really long journey, and if you think about it, even during the Pentium chip days, we actually had a CPU and the SRAM was off chip, and we created multi-chip modules. Then we had server chips that we joined at the bus, and we created multi-chip. Those are all, I would say, because of many physical limitations. But somewhere in the late 2000s, there was a transition to thin and light laptop. So we had the Haswell project. The Haswell project really wanted to build a CPU design which could power the thinnest, the most efficient laptops. And and I had the privilege and the honor of creating ultra low power chipset process, and then our team created a 2-chip MCP at that time. So you had the CPU and the PCH all integrated on the same substrate, and we were able to like make it work. And then we extended it, and we built platforms where we integrated EDRAM on the same substrate. So we actually, during the Haswell Broadwell timeframe, we have chips out there, hundreds of millions of chips, where the CPU and the chipset is a 2D MCP. We created a standard interface called OPI, or on-package interface, highly efficient. So we learned a lot. But then as we were going through our advanced process scaling, somewhere in 2014, so myself, Mark Bohr, and Rajesh, we were working on the process definition, and it kind of struck us that process scaling was getting very difficult. Some of the architectures were also like not seeing some of the benefits, and so at that time I came up with a process called P2.
By the way, just to couple of names Wilfred mentioned, Rajesh was one of the youngest Intel fellow at Intel, and Mark Bohr was basically the mastermind behind manufacturing technology at Intel, who all basically collaborated in this kind of thing. So just wanted to give the audience a flavor of basically who these guys are. Continue, please.
So at that time, so myself, Mark, and Rajesh, the first thing we did was knowing all the challenges that we are seeing, we created P1222, or it's also called now it's called Intel 16 or 22 FFL. So we took the best of all the different process nodes from Intel 10, Intel 14, 22, and we knew that actually there's a huge amount of value in leveraging both benefits from older nodes and benefits from newer nodes, and creating something which was not possible. So that gave us a platform of creating specialized chips. So as we were doing this, I realized that the old ways of doing MCPs, which are just 2D in nature, will not scale to high performance segments. High performance segments like data centers or AI, HPC, and eventually client. And myself, Mark Bohr, and Rajesh, we pitched the proposal of creating 3D chips in 2015. And at that time, Murthy had joined Intel, and he gave us the permission to build Lakefield. And we created a 3D chip, and we, through that exercise, created Lakefield, which gave us the opportunity to scale the technology in different dimensions. And that is where this whole idea of, not only creating a disaggregated architecture, but the right building blocks became real.
You did Lakefield, and then you did Ponte Vecchio, right?
So we did Lakefield, and there were other chips, and Ponte Vecchio, Meteor Lake, Arrow Lake, and other chips, yes, and all built, and we combine many of these technologies.
So when you did the first commercial processor using the basically disaggregation or chiplet technology, what were your main technology challenges in achieving the goals of basically what you wanted to achieve?
Okay, so good. So one of the things that we have always done is when we develop a technology, we kind of look at the roadmap. We wanted to pick a technology that would scale, a technology that will eventually become low cost, a technology that would give you benefit across a lot of segments. So to enable that, we really thought platforms and systems first. And what that really means is you can create, for example, pick a base die, and you could put different chiplets of a different architecture, and you can address many different segments. That's a client disaggregation architecture. For example, you can read it on hot chips, how we did that. Or you could look at Ponte Vecchio. So the base die comes with a fabric, cache, and different IOs, HBM. And you could put various chiplets, and you get different AI or HPC chips. So that's the first thing, is create an ecosystem and a platform. Then second is figure out how to scale that. For example, the bump pitch scaling. We think the bump pitch scaling in 3D technologies will go from 50, 36 down to very close to monolithic. So eventually this way of building chips will give you very close to monolithic designs, which will address things like cost, power, performance. The last thing that I want to mention is test. In the end, everything comes down to cost. Like having high yielding and the ability to test is super important. So we thought about this all right from the beginning, where we can actually make all this and we have this technique called known good die. Everything that comes together in a known good die format. That's not the only important thing. When you have many chiplets that come together, you have to break the exponential dependencies. Like for example, if you have 10 chips, you cannot have a compounding yield number. So we have methods of actually breaking some of those dependencies. So eventually, all these techniques can become mainstream.
So when you do 3D stacking or the chiplet aggregation, how do you handle the power delivery? Because that seems to be a big challenge, because the traditional methods of the power delivery to the chip will not work. Either you have to do backside power through silicon via and all of these things, right? So was the power delivery one of your major challenge in basically getting the whole thing work?
So Satya, you ask an excellent question. By the way, I've been very fortunate, having worked for the Oregon CPU team, to be involved in power delivery throughout my career. In fact, our team created ALM power gates. We created fiber on Haswell. So what really happened is when you create one of the solutions, power delivery is a really big problem. So when we built Ponte Vecchio, for example, we built it at 600 watt envelope. There's no product at that time frame which actually is a 600 watt. So we integrated a 3D power delivery, which cuts the ICC max coming in. So like for example, the R on the package, you do not need to be that exact. We can generate many rails. So what we see is that through a combination of integrated power delivery and motherboard VRs and the appropriate high voltages coming in, you can make this very close to monolithic. In fact, we believe that in the end, the delta between a monolithic chip and a 3D chip from a power delivery is going to be very small. But in the last decade, we had to invent many technologies to make it work. It has not been easy.
Okay. We learned that basically as the size of the chips are basically increasing, your verification, functional verification is becoming one of the most important challenge.
Yep.
So how does this manifest into a multi-chiplet environment, right? How do you handle verification? Basically, is it very similar to the way we handle the block level verification, or do you get different type of the challenges when you do basically full chip verification, including multiple chiplets and multiple dies?
Oh, a really good question, Satya. Let me tell you, I think, how we solve this. Just like, for example, in a chip, you have lib files and timing arcs. So, for example, if you have multiple blocks, you can sign off because each of the blocks has a timing arc, and you can close it. So what happens is if you can actually do complete isolation from noise, from timing, and from electricals, it just becomes like just a 2D chip. So essentially, across 3D partitioning, you could validate each of these chips, independently and put it together. The key question is, how do you do loop back testing of some of the interfaces, because many of the interfaces are at very fine pitch. How do you do clocking? Can you verify the clocking? There are some interactions in timing and power delivery that only become, so those are some of the challenges. But let me tell you some bigger challenges that actually are very interesting and need to be looked at. For example, many of these chips have a lot of firmware code, boot up sequences. How do you test it when you actually have repartitioned it? Do you need all the firmware at the very end? Can you do it on the chiplet? Those are all very important techniques, and they, if not done correctly, they manifest in the back-end validation, because it's only when the whole chip is assembled, then the boot up sequences and the firmware code is ready. So this is where emulation becomes very important. It's a double-edged sword. If you decompose it into many small chiplets, I think you have a better hand at emulating it. But there's also this questions like, do you get good coverage? Because, if you break up Humpty Dumpty, can you actually get a coherent picture of your thing? And this comes, I think, to this very important point. What are your interfaces? Can you standardize it? And do all these chips have a very unified view across this life cycle?
So coming to that point, right? Going in the future, the different chiplets of a large system may not come from the same company or the same source. They may come from the different companies, right? In that case, basically, how do you see the importance of things like UCI and other things? And is industry ready to adopt a basically unified interface which is agreeable by everybody, so that we can take chiplets from different companies and put together a system, right? So how do you see the emergence of the standards for basically chiplet interfaces when they come from different sources?
So let me address that. By the way, I've been fortunate to both create and bring different products which exactly have this. So first is Ponte Vecchio. Ponte Vecchio has chiplets, both from Intel and TSMC. And our client product family, Meteor Lake and Arrow Lake, which has chiplets from both Intel and TSMC. So there are definitely interfaces that are somewhat standardized. For example, on the client product family, we used CXL interface on the graphics. So CXL is more of a coherent interface where you can cut across memory boundaries or caches. So definitely there are interfaces where you can standardize and you can have accelerator attaches. Where it becomes very problematic is coherent, highly bandwidth and latency sensitive interfaces. I think that's where there's more work to be done. So I think the industry is going to evolve, but I think Intel, we have been ahead of this curve. We have products that have actually integrated chiplets from different companies, different foundry sources, different things. So there's a lot of learning there, and over time you'll see more of this.
So, whenever you partition a large system, right? Partitioning has always been basically a problem for optimization guys, that how do you find basically the natural cut in a problem to partition across basically different things. So how do we handle that basically into the chiplet environment? Do we just go by functional blocks, like basically the way the things happen in the board in a natural way? Or if the core itself is a very big, can it be cut down to multiple chiplets? And basically, how do we manage the large number of basically connections going from the one chiplet to another chiplet if you don't find a natural cut, right?
That is good. Okay, I think different market segments react differently to it, and I'll give you the full spectrum opinion. If it's a high volume, lower cost, where cost is important, this partitioning actually varies over time. So I'll give you some examples. For example, at the beginning of the process, maybe graphics is disaggregated, or some aspect of AI engine is disaggregated because you just want to get a product out. But as a product matures, you may want to integrate it. I think your integration technique should be very flexible. Where things stand the test of time in many of the segments is like I/O or non-scaling, blocks. Like for example, if you have a block which is a Wi-Fi block or a low-power chipset, you probably want to put it on a very different process, and that will always be a different chip. With high performance, the chances of getting reaggregated are high. So that's in a client SoC world. In a data center world, I see a very different trend. You want to integrate more and more silicon. You want to build, so both forces are at work. You want to build scale-up systems and scale-out. The scale-out is a very artificial problem because essentially you're only limited by not only power, but like the amount of silicon you can put in a socket. As you get, thanks to Moore's law, as you can integrate more and more, you are at the question is like, how can you, increase performance? And that is where you aggregate more chiplets in a given socket. And the interfaces there could be CXL, could be UCIe. As long as they're low power and high bandwidth, you can actually keep going and build larger and larger systems.
But taking a different track, right? Many research facilities are trying to basically integrate different type of the technologies on the same wafers. In the chiplet, you solve it by basically having a chiplet. One may be at 5 nanometer, one may be at 13 nanometer, one is memory, one is basically sensor. You have different chiplets for different things, right?
Yeah.
But many researchers like basically at MIT, Max and all those people are trying to do integration of various technologies on the same wafer itself, right? So how does basically the two different approaches of basically handling the different technologies on a single product, and how do you see the future of heterogeneous technologies on the same wafer?
Okay, excellent point. I think you'll have this for a long time, because there are definitely many powerful forces where you want to be a small monolithic chip, and you want to get, for example, some of the functionality that you would want, high voltage, thick gate. You may want some specialized memory. Definitely, it can all be created, and a small monolithic chip is very efficient to design. The supply chain of it is much more easier to handle. But then on the other hand, let's say your compute performance is absolutely important and you do not care for some of these interfaces, you definitely want to take a different approach. So different market segments will have different requirements. I think you will continue to see the trend where these different approaches will play out. In the long term, physics will determine which will win out. Definitely thick gates will not scale as well. Memory is not scaling. So all those things will eventually get disaggregated.
Now, another approach, right? The companies like Cerebrus have
Yes.
gone the totally other way, right?
That's right.
They said we'll make a whole 300 millimeter wafer as a single chip, right?
Yes.
Do you see the promise of handling very large problems using that approach?
Okay, so really, really good question. I think, first of all, I think you want to build a very balanced system. You cannot just integrate a lot of logic and not have access to memory bandwidth. There's also the question of how do you get traffic in and out of a wafer. There's also a question of how do you do the power delivery and cooling. There's also a question of cost and yield. So definitely what is happening is we are building chips which are larger and larger, multi-radical, and eventually they will get to a wafer scale. But the form of wafer scale in the end will be very different from today's generation because you want to be building those chips at really low cost and also the ability to get a lot of memory. For example, if I were to build an AI HPC chip, more than 70% of the silicon is actually memory, like HBM and SRAM. The question is, as that becomes more and more important, it becomes very difficult in a wafer scale approach and you lose a lot of efficiency. So you have to solve many fundamental problems to make some of these techniques more widely usable.
Sure. So going little bit higher up in our discussion, today wherever you go, any technical conference or basically any discussion around the semiconductor technology, basically most of the discussion centers around the chiplet, right? So how do you see the future of basically this technology? Is it panacea for all that basically chiplet is going to solve all the problems, or basically for different type of the applications we have to take different approach and judiciously use the basically chiplet approach? Because today we see the most successful implementation of the chiplet approach is very high performance, basically processors and things like that. So how do you see future going? Basically, will it percolate among all different type of the applications, or different type of the approaches will have their own basically their own place? So any thoughts on this?
So Satya, this goes back to, so when I started in the industry, I was both a custom designer and I was able to synthesize all the circuits. And it was actually a 20-year battle where finally the people who were doing the logic synthesis won over the custom designers. And there was a huge gap, where logic synthesis did not meet the expectation of many custom circuits. And even there today, you can design some custom circuits which are very, very efficient. So I think we're exactly in that debate. We're in a very early portion of the journey. I think chiplets work very well for high performance chips, very large chips, where you want to build larger and larger systems. I think the trick and the work that is needed to make them mainstream is to make them low cost, high yielding. We also have to improve the technology where the power inefficiencies, latency significantly improve. So that means, like for example, the bump pitch improves, the metal stacks, the process technologies to build all this improves. And also we have to build interfaces which are like really low power and high bandwidth. So I think we are in the very beginning portion of it. And I think it starts with high performance, and over time, and it will probably take some time, where it will percolate to other segments.
Sure. So obviously this looks like a very promising technology at the early stage of it, basically its implementation. How do you see this whole change in the methodology is impacting extension of the Moore's law, both in terms of the density and the cost per transistor.
Oh, great. By the way, you must be aware of generative AI and ChatGPT.
Absolutely.
So the Moore's law, obviously.
But it's only up to 2021, so I can't get the latest thing from the
Yes.
ChatGPT.
But let me. So Moore's law is doubling every 2 years.
Yeah.
But if you look at today's data centers that service AI, they want a doubling every 4 months. That's like insane. So actually, the important thing about packaging is it gives you this more than Moore's, because you can augment all this and get you additional transistors. And as long as you can feed the power and you can make it work, it's a compounding technique just by itself. And I think what you will see is, you will see more and more packaging technologies along with memory to be on this supercharged exponential, where you will try to cram more silicon and more transistors on this more aggressive cadence, because there's a lot of performance to be gained by training more complicated and bigger models, which can, work wonders. Not only that, but also these models which can become really low cost and more democratic in nature, where anybody can access them and train them.
Does we all understand the per area density will be benefited by the chiplet technology? Does it give the same benefit for transistor cost, per transistor cost? Like, can we say that it will help in reducing per transistor cost by half every 2 years?
Oh, very interesting question. So it all comes down to what's the future of scaling. Not all blocks are scaling very well. Logic scales really well. Analog, and when I say analog, like high voltage I/O may not scale well. SRAM may not scale well. So today, many of the chips are 40 to 50% SRAM. Let's say they become 70% SRAM, only 30%. And if that 70% doesn't scale, that's your, yes. So it all comes down to, do you have the right disaggregation techniques, and what does your architecture need? And I think future architectures need a lot of memory, and some of that memory will be on older nodes or more specialized memory nodes, which will give you this cost scaling. I cannot tell you exactly what fraction, but the physics suggests that that's the right direction.
Okay. So now, little bit moving from chiplet and disaggregation, as you talk to basically your industry colleagues from manufacturing, from basically AI guys and all those things, what do you see as the future of the semiconductor technology? What are going to be the most important technology aspect, most important use cases, most important applications? We always talk about the killer app, and killer app right now seems to be the AI. But how do you see the future evolving basically in the for the chip design semiconductor technology?
So great. By the way, I have had the opportunity to work both on CPU design and graphics. For over 2.5 decades, I've designed almost all the CPUs, and I worked on the GPUs. So if you look at the CPU and the GPU roadmap, there's a huge amount of performance upside. You can build wider and bigger machines. Same thing with the GPUs. You can build really highly efficient. In fact, I'm more excited about being in the industry when I joined 20 years back, because there is an immense amount of the exponential weighting, and this will come from not just logic, but things like new memories, power delivery, new thermals, new materials, and obviously packaging. And I think that there are many decades of improvement. So this is a very exciting time to be alive and working in the semiconductor industry, because you can build systems that were not possible. And in fact, remember, Satya, you built the Paragon system, and I've had the joy of working on exascale. But and the reason why people want to build this system, so let me give you this example of exascale systems. Today's exascale systems, it takes about maybe 4 basketball fields. You have 60,000 nodes, but the advances that I'm talking about in a decade, you can take that and you can shrink it and maybe make it into a wafer, like like a wafer size.
Absolutely.
So just the fact that in a decade you can have that much of computing power scaled down, and there are physics that are actually being developed, makes it like so very interesting and alive to be working on this problem.
And we have seen it, like
Yes.
Paragon for 1 teraflop, we
Yes.
used to have basically one big building of basically machines.
That's right.
Today the same teraflop can be done on the maybe mobile phone, right?
And Satya, so let me tell you some of the themes that are actually evolving. For example, there is obviously the single thread model, there is a vector, and now we have the systolics and vector matrix processing.
Many different architectures.
But
right?
what is happening is, as some of these things are getting unified, it's actually these architectures can service things like training, large language models, recommendation systems, HPC, and single thread. So whoever can actually create the right composable architectures will actually, those would be the winning architectures. And the key there is the right memory hierarchy, the right way of, sharing and, scaling them out. And there's more unification that is happening than diversification. And that along with it will bring a huge amount of, new workloads and benefit that was not possible before.
Okay. So I think last topic, you must have seen that in last 1.5 years, India has put very strong foot forward in terms of basically creating the incentive policies and the programs for developing the semiconductor technology and the chips and the talent in the basically country. How do you see basically that going forward, and what are the things India can do to make basically what I say have a seat at the table whenever semiconductor is talked across the globe, right?
Yeah. So Satya, so this again goes back into my days, even in high school. I actually have in my house all the TTL chips that was there, so starting with the ALUs, all the entire 7.4 series, the BiCMOS. But the number of analog transistors, the SCR, the thyristors, the fan motor control, and the diodes, and the resistors. So I had about maybe 20 or 30 chips, but this huge rack of analog components. And you know where India can shine? It's this thing where you mix the analog components with mature semiconductors to address many segments, like from Wi-Fi, power delivery, solar control. For example, if I were to just think about it as I'm walking around, I want to know what's happening, what restaurants are there. You have like Wi-Fi coming up with the ultra wideband. And you know what, Satya? You don't need the most advanced electronics. You need mature processes like 28 nanometers or 65 nanometers or PMIC-like process sensors. I think there's a huge opportunity to build a huge ecosystem around it, which can power the billions of people, billion plus people that we have in India. And I think that is the segment that
today we became the most populous country in the world.
That is right.
Yes.
Yes.
I think this augurs well.
Yes.
Thank you so much, Wilfred. Any last comments or advice to the audience, especially the student community, which is taking up basically or want to take up this as a career? What should basically the advice for the young talent which is just entering this field?
So Satya, so good that you asked. So actually, when I went to engineering, I had the opportunity to take computer science or programming or software. I actually just wanted to work on the hardest physics problems. It's only when you actually understand the critical circuits, the critical material science, the where, and then you actually can come up with the right solutions. What I would encourage every one of you who's actually aspiring to be an engineer to know the fundamentals, know your physics, know your material science. Thermals are important, power delivery is important, knowing how those transistors work is very important. Once you understand those fundamentals, over time you can build software models around it, and that's what I did. And I think the people who would actually be very powerful and have a seat at the table who will understand all these pieces and can put complete systems, and knowing fundamentals is very important. And I think that is sometimes I see lacking. In fact, when I go around and I talk to people, they all are very interested in showing me problem, but I do not know how to get to the next level. So it's super important to be, like aware of the fundamentals and work on it very hard. And that's what I would tell everybody to focus on, and you'll have a wonderful career.
So thank you, Wilfred, and we are all proud of you for all your achievement. And I feel honored that basically I was working with you early part of your career as a senior during the Intel days. And thank you everybody for joining us for this episode of Chip Pe Charcha. We had a wonderful discussion with Wilfred, and we will bring more such global technology leaders to discuss important aspects of the VLSI chip design and semiconductor technologies in the future episodes of Chip Pe Charcha. Thank you so much and have a good day.
Thank you, Satya. Thank you all.